Hello everybody. Today we're going to be talking about Riemann sums, mostly because I have a test on it tomorrow, and if you're taking AP Calc like A, B, or BC, um, because it'll probably line up with that pretty soon, and you guys will probably have a test on it soon. So I guess first I want to go over right hand sums. Right hand sums. And these are rectangles. So let's make a table, right? Maybe one, two, here, right? And let's say this is x and this is f of x. So let's say x is 1, 2, 5, and 6. Now let's say f of x is 3 there, maybe 5 here, 8, and 10. So if you're doing a right-hand sum, now keep in mind these are rectangles, right? And so what we're doing for this is let me just make a graph here. Think of that as the graph paper, right? And then let me pick a different color. Sure. That is not a different color. Um, let's pick a different color. So like this, right? Now, if we're going like to 1, right? Let's say this is 1, and we're making a rectangle, right? So this is the height up to there, and this is the base, and the area of a rectangle is height times base. So area equals height times base. And so if the base is from the origin to the point that we're looking at, that would be 1 for this example. So for this example, it would be area equals h times 1, and h would be where f of x is. And so for this table, that would be area equals 3 times 1 for that rectangle, sorry. So it'd be 3 units. Now, okay, let's remove this. Okay, so now let's talk right-hand sums. So now that we know that the base is the change in x, so delta x, right? And the height is f of x at whatever point we're looking at for the rectangle. Now we can find the right-hand sum. So the right-hand sum is taking the right endpoint of each subinterval. So here our interval, that's a little thick. Here our interval is 1, 2, 6. And we have 3 subintervals, so 1, 2, 2, 5, and 5, 6. So if we're taking f of x at the right-hand point of each of these, so it would be f of 2, this would be f of 5, and this would be f of 6. And so, and what's that? F of 2 is 5, f of 5 is 8, and f of 6 is 10. So keep in mind, that's your height for these 3 rectangles. This is 3 rectangles. 3 subintervals means 3 rectangles, all right? And so area equals h times base. So since there's 3 subintervals and 3 rectangles, there's going to be 3 different areas, and you're going to have to add each of them up because it's a sum, right? So we get that so since there's 3 areas, you get delta x, which is b, right? Remember? So I guess we can just write, right? I guess we can just do it. Delta x times 5, because that's the height for the first rectangle, plus delta x times 8, because that's the height for the second rectangle, plus delta x times 10, because that's the height of the last rectangle. So from here, we're going to want to find delta x for each subinterval. So since the height of 5 is going to be the rectangle from the interval of 1 to 2, well, delta x is the movement from point 1 to 2, which would be you're moving 1 unit to the right. So area would equal 1 times 5 for the first rectangle. For the second rectangle, you're moving from 2 to 5, so delta x would be 3 times the height of 8 for the area. And then for the last one, you're moving from 5 to 6, and that would once again be 1 times the height of 10. And so what does this equal? Well, this equals 5 plus 24 plus 15, which would be 39 units, whatever unit that's going to be in. And so that's a right-hand sum. Now, okay, now that we have that, we can erase all of that. So we're going to analyze a graph, all right? If we have a graph here, and the graph it looks like this. Now, would the right-hand sum be an overestimate or an underestimate of the actual area? So let's say the area to here, right, which would be this shaded area. So would a right-hand sum be an over or an underestimate? I'll give you guys a minute to think about it. Okay, so the right-hand sum would actually be an overestimate. Now, this is because the function is increasing. Okay, so the derivative at each of these points is positive. So keep in mind, the derivative of a function being positive means the function is increasing, right? So you could say f prime of x is greater than 0. And you can see this because you take the right hand height, and let's say you have two endpoints for this rectangle, right? There and here. And so that area is greater than this area. So the total area is greater than the area that's just under the curve. And so therefore it's an overestimate. Now the opposite is also true, right? If we have a function that's decreasing, so like this, then a right-hand sum, let's say we go from here to here, a right-hand sum, a right-hand sum would be an underestimate because you're not getting this triangle in there, right? And so you say f prime of x is less than 0. Okay, so that's that. Now we can move on to left-hand sums. But first, I'd like to do this. Okay, cool. Okay, so let's say, left hand Riemann sums. Now let's make a table again. Say, no, here, I'll do it like this. Say this is x, and this is f of x. So I guess we can do 1, 2, 5, and 6 again. So we can say 3, 5, 8, and 10. Okay. So the interval is from 1 to 6. But there's 3 subintervals. Once again, it's the same subintervals, 1 to 2, 2 to 5, and 5 to 6. So if we're taking the left-hand sum, well, think about it. For the right-hand sum, we took the height of the right endpoint. So for the left-hand sum, we would take the height of the left endpoint. So this would be 3 for the height, 5 for the height, and 8 for the height. And so you would go area, once again, and since delta x is the same, right, it's the movement in position, which is 1, 3, 1. So it would be 1 times 3, because that's the area of the first rectangle, plus 3 times 5, that's the area of the second rectangle, plus 1 times 8, which is the area of the third rectangle. And so what's this? This is 3 plus 15 plus 8. So that's going to be 26. So from here, we can do the same thing that we did for the right-hand one. Let's draw a graph, okay? Sorry, that's a terrible line. So let's say we have an increasing function like this, like we had for the right-hand sum. Now, let's say, let's say that that's one endpoint and this is the other endpoint. Well, if you're taking the left, this would be the height. And so that would be the area of that rectangle, and we'd be missing this area. So for this, if g prime of x is greater than 0, or sorry, I guess it would be f prime, because I want to stay consistent here, then the left-hand area would be an underestimate of the actual area. And similarly, we can do this again. If it's a decreasing function, and we do this, then the left-hand sum would be an overestimate. So if f prime of x is less than 0, then it's an overestimate. Okay, so that's that. Those are left-hand and right-hand sums. I hope this has helped so far. And of course, if there's any questions, I'd be happy to answer. So let's go back here. So now let's talk about trapezoidal sums. Okay, so there's going to be a trapezoid, right? So let's draw a function again, or same values, right? X, f of x. Okay, and we're gonna go like this. So this is gonna be 1, 2, 5, and 6, same values. 3, 5, 8, and 10, same values again. So we know that we have the main interval of 1 to 6 and the subintervals of 1 to 2, 2 to 5, and 5 to 6. So when we're looking at this graph, now let me graph this out over here. So we'll have the line. Maybe we'll say that this is 5, this is 8, and this is 10, and so on. This would be 2, 1, 5, and 6. I know it's uneven, but that's just how it's going to be. So a trapezoid, right, would be like this. And then another one would be from 2 to 5, it'd be like this. And then a final one would be from 5 to 6. Sorry, that's a terrible line. So that one would be like that. Okay, and so the area of a trapezoid, I hope you remember this, is 1/2 of base 1 plus base 2 times the height of the trapezoid. So what are the bases, right? So base 1 would be the height of 1. So for this blue trapezoid, it'd be the height at 1. Base 2 would be the height at 2. So that would be f of 1 plus f of 2 for this example. And for the green triangle, it would be base 1 would be f of 2, and base 2 would be f of 5. And so then for the last one, base 1 would be f of 5. So for the purple trapezoid, and base 2 would be f of 6. And h, actually, for this one, h is not f of x, but it's delta x in this example. So that would be like 1, right? 1, 1, 3, and 1 again. So, okay, now that we know that, let's try this. Okay, so base 1, let's say base 1 and base 2. Well, base 1 would be 3, base 2 would be 5, base 1 would be 5, base 2 would be 8, base 1 would be 8, and base 2 would be 10. Okay, so now that we have that, there's going to be 3 trapezoids. So we just add the areas up, right? So area equals 1/2, and this is for the first rectangle, of 3 plus 5 times 1. So since delta x is 1, and then for there it's 3 and back to 1. And then you're adding the area of the next trapezoid, which would be 1/2 of 5 plus 8 times 3. And then you're adding the area of the last trapezoid. So 8 plus 10 times 1. And so this equals 4 plus 39 over 2 plus 9, which is 13 plus 19.5, which equals, what's that, 32.5 units. And so if you look at this graph up here, let's go back to this graph up here. This is a much better approximation for the area than the other, like the left-hand sum or the right-hand sum. You can see, like, I mean, obviously it's not perfect and you shouldn't write equals. In reality, the area should be more like approximation lines, right? So squiggly lines. Because it's not equal, but it's much better. Now, let's talk about whether this is an overestimate or an underestimate. So, okay. Let's say we have a graph like, like this, and you have a trapezoid. You have trapezoids, sorry. I guess you could draw it. It'd be better visual representation if I went something like, oh, right? So I think you can tell that's an overestimate, right? But let's see what else is also an overestimate. So is this going to be an overestimate? Well, we'll have to see. So height 1. Let's just go to here for effect. So that's also an overestimate. But you can say, Well, okay, but here the function's increasing. In this one, it's increasing. But in this one, it's decreasing. So why are both of them overestimates? And the reason is because f double prime, so the second derivative, is greater than 0. It's concave up. So trapezoid, like being an overestimate, has to do with concavity. So it's an overestimate if it's concave up, or we'll be able to see this if it's concave down like this. A trapezoid would be an underestimate, right? Your missing area there, missing area. So in this case, f prime prime is less than 0. So if it's concave down, it's an underestimate. And if it's concave up, it's an overestimate. Just keep that in mind. Okay. Now, that's good and all, but we need to talk about getting the actual area under the curve. So how do you do this with limits, right? Before we get into integrals and all that, which I'm sure you want to get into, but you can't do that immediately because the AP test, or, you're just going to have to know it, right? The AP test, you have to know it for that. So how do you get the accurate area? Well, the way I see it is you'd get the accurate area if you had an infinite number of rectangles, right? Imagine if each rectangle is infinitely small. You'd be able to get so many that you'd get the area right? Like each of these is a rectangle. Well, that looks much better than if you go like this, right? Seems pretty better to me. So how do you do that though? Well, how you do that is you would have an infinite number of delta x, right? Like an infinite number. So if you're having an infinite number, how do you get an infinite number of rectangles under a finite interval, right? Well, you would have to use the limits, right? The limit as we would say n goes to infinity, and n is the number of rectangles. So this makes sense, right? If we want infinite rectangles and n's the number of rectangles, then we want n to go to infinity. Makes sense. Okay. So how do we get like the width of the rectangles, right? Because they're infinitely small, but the like it can't just be nothing, right? Like infinitely small in what way? So how we do that is you have your interval a comma b is your interval. So for our examples, it was 1 to 6. And so the width, well, if you go over this, then, so like let's say you do, the width is 7, right? Let's say that's what you make, 7 over n, because you're gonna, like, if it's 7, I mean, it's kind of hard to explain. Basically, well, okay, let's say it like this. Basically, how you do it, let's not say how you don't do it. So how you do it is you have b minus a over n, right? And it's because if you do any other way, you're not going to get an accurate number for the area. It'll be like sad, and your teacher will yell at you, and the AP exam won't be happy. And so for this example, this would be 6 minus 1 over n, which would equal 5 over n. So what do you do with the n, right? You got to find the area somehow. Well, this would go into your limit, right? 5 over n. Now, yes, that would go into the limit. But first, well, now you want to think about the height, right? You have the width of each rectangle. So what's the height? Well, you may be tempted to say that it is f of 5 over n, right? But that's not true because then that would be one value. And like you can see here, for this rectangle, it's one value, right? For this rectangle, it's a higher value than this rectangle. So it couldn't be 5 over n. No. And so you might be tempted to say, like, well, you do 5 times which rectangle it is. So like, let's say 5 times k over n, right? So like the third rectangle or something. Um, and you'd be closer, right? Because that would get you a higher height, or well, depending on what the function is, it would just give you a different height than the previous rectangles. And so you'd be like, okay, that's close, that's close. But you're not quite there because we're starting at the first endpoint. So we're starting at 1, right? So you can't just have this. So you'd have to start at 1 plus 5k over n. So what does this mean? Like if you start at 1 plus 5k over n, that's the height of the first rectangle. And then if you do, well, the height of the first rectangle would be when k is 1. So 1 plus 5 over n. And so for the second rectangle, it would be 1 plus 10 over n. You're just, k is like, you're moving on the graph, right? And so that's how that works, right? And so then you might be like, well, you need to add up all of the areas, right? So let's keep in mind area equals base times height. And so for this, the area would equal our width, right? Our base. So 5 over n times f of 1 plus whatever rectangle, right? So f of whatever rectangle. So, but there's an infinite number of rectangles. So what you have to do is take the sum of the height, right? I know it's a poorly written sign, but you're taking the sum of the height. You're saying k equals 1 to n, because n is the number of rectangles, so k equals 1 to the number of rectangles, that's how many rectangles you have, of f of 1 plus 5k over n times the width, and then that'll give you the area. So what are you doing with this? Well, keep in mind that we wrote a limit earlier, and you're doing the limit of this. So it would be the limit as k equals 1 to n of f of 1 plus 5k over n times 5 over n. Okay, so this is a constant because, so 5 over n is a constant because you're doing this with like respect to k. So you can take it to the front, right? And so let's say f of x equals 1, right? And so then you would go the limit as n goes to infinity of 5 over n times the sum from k equals 1 to n of, well, if f of x, oh, I'm sorry, not 1, that's not what I meant. I meant to say f of x equals x. So from k equals 1 to n of, well, if it's f of 1 plus 5k over n, well, then it would just be x, you'd substitute for x. So from 1 plus 5k over n. And so what is that, right? So this would go to the limit as n goes to infinity of 5 over n. And now you have to remember your sum rules, right? Or yeah, your sum rules. So a constant in the sum is just the constant times the top limit. So this would be n plus, well, when it's 1, it's n times n plus 1 over 2. And you'd multiply this by 5 over n because that's what k is being multiplied by here. So you go times 5 over n. So this would be 5n times n plus 1 over 2. 2n, sorry. Okay, so now how do you evaluate this limit? Well, let's get rid of some of this for space. So to evaluate this limit, let's remember the limit rules. So you go to the limit as n goes to infinity. So you should substitute the 5 over n. So this would be 5, or distribute the 5 over n, plus 25n squared plus 25n over 2n squared. And I'm sorry, it's kind of slanting. And so if we remember our limit to infinity rules, this would just equal 5 plus 25 over 2, because these are the same exponent, which would equal 17.5 units. And so that's the actual area. So the area equals 17.5 units from 1 to 6 of x, right? The function x. And so it's not an approximation, right? It's an actual equals. This is what the area actually equals, so it's not an approximation. And so that's all I have for these sums. Thank you for watching, and I hope this helped somewhat, right? Thank you.